Hey everybody, this super cool, great, awesome, amazing video is to show you how to do the FET Energy Force Lab. So let's go over here to our purple folder, the Energy Force Motion folder. Click on the Force folder. After that, once you've clicked on that, you're going to click on the FET Force Activity. Once you've seen the FET Force Activity, the next thing you're going to do is click on this super cool little thing here where you can either download the document like this and open it up and type in it, or you can just view it online. Either way, you're going to need to click Enable Editing up here, and here is the link for the FET website. So I'm going to go ahead and just copy it. Copy. Go on over here and go to where the activity is located, and I'm going to paste it. By the way, this is going to be where we put the activity when we are done with it. So we are going to, first thing, according to the instructions right over here, is we are going to follow these instructions. So I need to select net force. Cool. Click net force. Then from here, I just follow the instructions. It says to create a scenario on the rope pull to where the sum of the forces is balanced. Okay, let's throw this guy up here and this guy right here. Now it's a balanced amount. I just need to click on these little boxes here so I can see. Pulling, okay, cool, it's balanced. So then what I'm going to do is right over here, I'm going to type how much the newtons are. Okay, cool. There's a million newtons over there. And then I'm going to go over here, oops, not over there, and go to the end of this thing and type right over here, newtons to that side. If you're really cool, you can type inside of here. I can't, but maybe you are really cool. Okay, so the next thing that it says to do is that it says to, so you're going to find the net force by taking a look at the sum of forces. Oh, look, it even says that in the instructions right here. Sum of forces is our net force, and you're going to go ahead and just type that there. So I'm looking at my sum of forces. It's currently 0. So I'm just going to type in sum of forces equals 0 newtons. Okay, next I'm going to go down here to create a scenario on the rope pull in which the forces are unbalanced. So for finding an unbalanced force, all I have to do is add another force to the rope pull. And here you go. I'm going to go ahead and click pause. You can see that the newtons to the right is 150, newtons to the left is 100. Go ahead and fill those bad boys in their appropriate locations. And then I've got that my sum of newtons is 50 newtons to the right. Good job, red team. You won. Now let's scroll down just a little bit further. Part 2, motion. Click on the motion tab. Play around with the simulation so that you know how to make it work. Awesome. Let's go down here to where it says motion tab. Clicked on that. Now I'm going to go ahead and play with the simulation. Cool, I can push on M. Cool, I can push in this way. Oops. That's really neat. Yeah. Okay, cool. So then what I'm going to do is I'm going to make sure all the boxes are checked. Check. Checkity check. And then I'm going to note that there's no friction in this scenario. That's why this guy keeps on rolling. I'm going to place the refrigerator on here, remove the box, simply following the instructions on the paper. And then I'm going to apply a force of approximately 100 newtons. Cool. So apply 100 newtons. 100-ish. All right, then let go. Once the skateboard is moving, let it go. Answer the following questions. What happens to the speed of the skateboard refrigerator when there's no longer force being applied? After the force has been applied, what's happening? Does it increase in speed? Is it staying at the same speed? Then you're going to type that answer there. Okay. Are the forces acting on the skateboard balanced or unbalanced? Well, there's not really anything acting on it, so put my answer there. All right. What are the forces acting on the skateboard or refrigerator? You can take a look at your notes. I can tell you right now, I've got applied forces here, and it's just continually moving. Fabulous. Going to go ahead and type my answer in there. Next, will the skateboard refrigerator ever stop moving? Why or why not? So what do you think? Does this guy look like he's ever going to stop moving? Put your answer in there. Cool. Let's go ahead and speed it up a little bit. because I always like fast speeds. All right, 10.6 meters per second. Now we're really cooking. Okay there, question number 2. Reset the simulation and click all the boxes again. Solid. Reset. All the boxes clicked. Okay. Switch the box with the refrigerator. Place it up there. Now apply a force of approximately 100 newtons. This time, do not stop applying the force to the refrigerator / skateboard. Answer the following questions. What happens to the speed of the skateboard or refrigerator when the force is continuously applied? Well, what's happening to the speed up here? Okay, go ahead and type your answer right there. Next, are the forces acting on the skateboard balanced or unbalanced? Well, I just have to look here to see the forces acting on the skateboard and identify whether or not they are balanced or unbalanced. If they're balanced, there would be evenness. If they're unbalanced, there would be not evenness. Okay, go ahead and type in your answer right there. Next, will the skateboard refrigerator ever stop changing? Why or why not? Well, will it ever stop going up in speed? Interesting question. Type your answers right there. Cool. Part 2, friction. Click on the, should say friction tab. So we're going to go down here to the friction tab. Cool. Play around with the simulation so you know how this one works. All right. Push, 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 push. Okay, cool. Click on all the boxes to make sure they're on. All right, cool. Next, how does the presence of friction affect the movement of the object on the simulation? So how does the presence of friction affect the movement of these objects? What does it do? In case I need to look again, I can always do one of these numbers here where I click on the thing. Or I can just click this and see. Okay. My answer there. Neato burrito. Next up, before the object starts moving, what do you notice about the frictional force and the applied force? Are they balanced or unbalanced? So before it's moving, is it moving right now? No. No, it's not moving right now. So what do we notice? Okay, you're going to put that there. And then are they balanced or unbalanced? You're going to put that there. Next up, I've got number 3 here. After the object starts moving, what do you notice about the frictional force and the applied force? Are the forces balanced or unbalanced? So my applied force is still at 150 newtons. My frictional force is now down to 94 newtons. That's interesting. Let's look at that again. So 50, 100. Did you see that? I don't know if you saw that. I'll show you one more time. Watch the frictional force when it starts to move. See how it dropped down a little bit there? So that frictional force did slow it down quite a bit there. That's pretty interesting. And then were the forces balanced or unbalanced? Type in your answer there. Remember, if it's balanced, it's going to equal itself out. And if it's unbalanced, then it's not. Okay. Number 4 here. Place one single 50-kilogram box on the ground. How much force is required to put the box in motion? Well, how much force do I have to add? Then I know that 150 gets it in motion, but it's not exact. Let's find out what our exact number is. Interesting. So I'm going to go ahead and type that number in for number 4. Then I'm going to place a second kg box or kilogramical box on there. I am going to predict exactly how fast it's got to go. All right, guy, you're going to have to move. Cool. So now that I've done that, I'm going to make my prediction. Let's say that it's 300 newtons to make it go. That sounds like a good guess. You know what? Let's make it 500 newtons to make it go. There we go, 500 newtons. What's the actual force required? Well, let's find out how much it actually takes for it to move. 50, 100, 150, 200, 250, 300 is when it starts to move over here. Well, that's pretty neato burrito, but that's not enough for me. No, sorry, Bob. Let's go back up to 250. And let's put it up individuals until we get to the proper number, okay? We're going to go ahead and type that number right here. Next, how are these two forces related? How are applied force and frictional force related? Super cool. You're going to put your answer in right there. Can you use this to predict how much force is required to move the refrigerator? Put your prediction. Let's move you out of the way here. Move and move and move and move and move. Refrigerator up. I see it's 200 kgs. Let's say that it's going to be 25. 1, 2, 3, 4, 25. Well, doesn't look like 25 newtons is doing anything. Interesting, interesting. Let's pump up the jams. Pump up the jams. Pump it up. Wow. The actual is greater than 500. Finally, we've got our challenge. Challenge. For the challenge, we're going to find out just how much this box here weighs. I'm going to apply force to it until I can get it to move. All right, it seems to move at the 150 mark. That's pretty neato burrito. Dorito. Let's see what else moves at the 150 mark with 56 left. Here we go, 150, not moving. How about this nice old man? Not moving. How about this nice young man? Moving, but 75 newtons, not 50 whatever. Interesting. Let's stop. And now let's try 150 on this. With 56. Was that the same number as we had for the box? I don't recall. It was the same number. Wait, Sawchuck, how did you find that? Okay, I'll show you. So I'm applying the same amount of force as I was before. I'm seeing what the sum of my forces is, the total newtons, because the frictional force is the same and the applied force is the same. And then I'm comparing that to the other thing to see what its total forces or sum of forces was, because the frictional force is the same, the applied force is the same, and my total force is net force is the same. So now I'm just seeing how much weight was there. That's the only variable I didn't know before. Wow, that's really neato burrito. Thanks. So then I'm just going to type my answer in right there. Finally, for the identification piece, you're just identifying whether these are contact or non-contact forces, and you are filling it in to each of those boxes. Once you've done that, you're going to save it. Okay. Thanks for the savey button. Save as force motion basics number 1. Cool. Now I'm going to close that and upload that bad boy to Schoology. Yeah. Once I've uploaded it, it'll be right over here, and I'll get all my points, and then I'll be a happy camper and have a great Thanksgiving break. I hope you get this done and get an A.